welcome back. So, this is our 26th lecture in the series, and as always let me begin with a recap. So, I am going to show you what we did last time, a quick glance through it. So, in the last lecture we looked at the title was examples of junction tree construction, and first what I actually did was I stated a theorem in which I actually stated that if the local domains can be organized into a junction tree, then that junction tree will have the properties of a maximal weight spanning tree. So, that means that in order to try to construct a junction tree, it is logical to start by trying to construct a maximal spanning tree. If that maximal spanning tree is a junction tree, then okay, then you are in then you will have a if that maximal weight spanning tree satisfies a certain inequality, as it turns out, then you actually get a junction tree, and we went through that last time. The particular inequality is that the edge weight of the graph that you construct must have the property that it is less than or equal to the node weight of the graph minus the number of variables. Okay, so, that was the first thing. Then we looked at an example, although I did not show you how we arrived at this construction. I showed you an example of this, and then so we proved that, then went on to some examples. The first example had to do with one of the computations that I introduced early on. There were two functions of certain 4 variables, alpha and beta, that we actually had to compute, and I showed you how one could go about constructing a maximal weight spanning tree. And when we checked the criterion at the end of once we finished constructing the maximal weight spanning tree, we found that yes, it meets the inequality that is required to be satisfied is satisfied. Therefore, what you have is a junction tree. And then we looked at a second example involving the 8-dimensional Walsh-Hadamard transform, and there we found that actually a junction tree cannot be constructed. The reason being that when the maximal weight spanning tree fails to satisfy the equality, and therefore a junction tree simply does not exist, at least when constructed using the technique that we have outlined. Another side comment that I made is that in constructing your junction tree, that is you are going to we invoked a greedy algorithm, and the particular algorithm is known as Prim's algorithm, which attempts to actually add a node to existing subgraph by which has maximal weight, okay, which is connected through an edge of maximal weight. And sometimes you have more than one choice, and I pointed out that it turns out, and we will not actually prove this in the class, so I will just state this without proof. It turns out that the edge associated with a particular edge, that the cost, the computational cost associated with a certain edge is given by this. It is the size of the alphabet to the node on the left, size of the alphabet to of the node associated with the node on the right, minus the size of the alphabet associated with the intersection alphabet, which is this. So, in case of ties, you can use this criterion, that is minimization of this criterion, as a way of breaking the ties. Okay. So, I think that is about where we were, and what I would like to do today is continue that, and we will look at an example, and then the title is message passing. So, we will also see, once you constructed the junction tree, what next. It turns out that the next step is to actually pass messages, and we will see how that is carried out. Okay. So, here is a recap. Let me just adjust my setup a little bit here. Okay, very good. So, recap. So, we first completed proof, showing that a junction tree, if the local domains can be organized into a junction tree. So, there is an if there, is necessarily, so I will just put IE, is necessarily a maximal weight spanning tree. And then we said that we would invoke Prim's algorithm. I will write greedy algorithm in brackets, to construct a maximal weight spanning tree. So, perhaps I should abbreviate this. Let us just call this an MST. Now, in the literature, MST often is used in the sense of a minimal spanning tree, but there is not much distinction, because you change the sign of the weights and you can go from a maximal weight spanning tree to minimal. So, there is no real difference there. So, we would invoke Prim's algorithm to construct an MST. So, we looked at examples. The example of a simple computation, or a pair of simple computations. And then we looked at the Walsh transform. And we saw that for the first example, we were in fact able to construct a junction tree. However, in the second, a junction tree, as according to Prim's algorithm, cannot be constructed. Okay. And then that brings us to our next example, which is that of our 742 code. So, the third example is our 742 code, and this code has the following parity check matrix. And if, for example, let us say we were interested in trying to decode the fourth code symbol in a particular instance, given the entire received vector P of x4 given y, this we have shown earlier that this can be computed according to, you can pass on to a computation of this type. So, as before, this sign indicates that it is proportional to. So, we want to compute this, and so what we actually do here is that you can so I have skipped a couple of steps, but basically you pass on first of all to the joint distribution, then you treat this as a marginalization. So, it is the joint probability of x and y, and then you factor that into y given x and p of x, and then again you invoke the proportionality constant again and put the indicator function of the code. So, this function here is 1 if x belongs to the code and 0 otherwise, and this is all straightforward because this factors like this and this factors like this, and you have this sum. And as I pointed out earlier, this wiggle in front of x 4 means that this is what we call a not sum, that is, we sum over all the variables x j other than x 4. And from this the local domains become apparent. So, I will just list them again. So, the local domains are each of the x j, j goes from 1 to 7, associated to p of y j given x j, then you have x 1, x 2, x 4 So, here these are the local kernels. Okay, so, we have our so with this we have covered all the local kernels that are there. There is one local kernel associated to each variable x j sitting here. Again, you disregard, you do not pay attention to the y sub j because they correspond to a particular realization. You have 1, 2, 4, 3, 4, 6, 4, 5, 7, and I have put them all down. Then insofar as organizing these into a local domain, I think I am going to just okay, so perhaps we should draw it, since we want to illustrate we can take advantage of this to illustrate the greedy algorithm. So, so we can start with any arbitrary local domain. Let us say that I start with the local domain 1, 2, 4, and I want to employ Prim's greedy algorithm, which says try to maximize your edge weight, but then I have the side criterion which says that you try to also minimize this quantity over here, which is q of S I, that is the alphabet to the left plus the alphabet to the right minus the alphabet of their intersection. So, I want to keep an eye on that as well. So, here my choices are these, and of course, in the interest of maximizing edge weight, I can connect this to either 3, 4, 6, 4, 5, 7 or 1, 2 or 4. But from this point of view, since the intersection is going to be 1, right, the intersection is 1. So, this thing is of the same size no matter what. You are trying to minimize this, and it becomes clear that you should connect to either a 1 or a 2. So, we will connect to a 1 over here. And then continuing in this way, you see that you could connect to a 2, to a 4, and this. Now, at this point the 4 has intersection 1 with either of these. So, you could introduce either of these and the cost is the same. So, there is nothing much to choose there. So, we will put down 3, 4, 6 here, connect this, and here you can tag on 3 and 6 and 4, 5, 7, 5 and 7, which is exactly. So, this time we have employed Prim's algorithm. You can check that all your edge weights are 1, because the intersection has always been 1. So, the node weight, of the graph is 7 plus 9, which is 16. The edge weight is 9. So, the node weight minus the edge weight is equal to 7, which is equal to the number of variables, and we saw this earlier. So, this is in fact a junction tree. Okay. All right. So, now what I am going to do is I am going to, this part over here was a repetition from an earlier lecture. So, I am going to, I just put that down just to jog your memory in a way. So, let me get rid of that. So, this is a junction tree, and I also will not be needing these edge weights. So, this is our last example of, and I just want to draw this graph again on the next page. So, let me cut and paste it. All right. So, as I said, this was our last example. Our next goal is, I just want to move it to the center a little bit. Let us see if I can do that. Okay, that is good. So, so what we have done, just to recap very quickly and give a broad overview, we have actually stated that there is a certain problem called the MPF problem, where you are given the objective is to marginalize a certain product function. And then we said that the first step that we will actually do is to actually identify the local domains and the local kernels, and then we will try to see if we can organize the local domains into the structure of a graph which is known as a junction tree. Now, sometimes that is possible, sometimes it is not. Okay. So, now let us assume it is possible, like in this particular example. Then the next step in actually computing the objective functions, so in all of these there could be multiple objective functions, each associated with one of the vertices, right. So, if you go back to our original formulation of some time back on the GDL, let us see if I can bring that back. Yeah, here we go. So, this is the setting of the MPF problem, and you see here that here is an example of, so over here what you actually have is the global kernel, which is the product of all the local kernels, and you are trying to marginalize it, and you could have one objective function associated with one local domain. You could have as many objective functions as you have local domains, and you are, so this is what you are trying to compute. So, getting back here, so what is your next step in trying to compute this objective functions? So, the next step is message passing. Okay. So, step 1 in solving, and I should put where possible, the MPF problem is to organize the local domains into a junction tree. Step 2, pass messages along the edges of the junction tree in accordance with some schedule. So, we will come to this issue of schedule a little later, but let us just focus on the word message here. So, the question is, well, what is the message that you are planning to transmit between the nodes? So, in general, let us say that you have a node x s I and you have a second node x s j, then the message between them that you will pass, okay, will be, first of all, we will designate that as mu I j x of s I intersect s j. Okay. So, that means that the message that is passed between the two will be only a function of all the variables that are common to both of these local domains. What exactly is the expression? The exact expression is that mu I j of x s I intersect s j is equal to the sum over x of s I minus s j of alpha I x s I times the product of j in I should change that, let me make that a k here, times the product k in n I, k not equal to j, of mu k I of s s k intersect x s I. So, this then is the message that you will pass. Okay, so what does that mean? Okay. So, let me expand this figure a little bit on the next page. So, what you have in the figure is that there are other nodes that feed into this node. So, you may have a generic x s k and you may have other nodes, and each of them in turn is going to pass on a message to this node, and that message will be mu k I of x of s k intersect s I. Okay. So, all that we are saying, and then there is another message that is also coming into this node, which is the particular local kernel of this node. So, from a graphical point of view, it is very simple. We are just saying that the message that is passed along this edge is simply the product of all the incoming messages to this node times the value of the local kernel. One thing to keep in mind is that there is no memory in this system, in the sense that the message never depends upon what happened, what messages were passed in the present. So, it could happen in a network that you will continuously be passing messages between nodes, and initially you might simply be passing the wrong message simply because the incoming messages are not correct. But eventually what will happen is that there is a spreading of knowledge throughout the network. So, eventually each node is going to acquire whatever knowledge it needs to acquire, and then it will have the right message to pass on here. and that will then continue to propagate down the network. Okay. Okay, so the message in a nutshell is just simply the product of all the incoming messages multiplied by the local kernel, and there is an additional key step, okay, and that key step is a step in which involves marginalization with respect to what? Well, you see that in this junction tree, on this side you have variables corresponding to Sj and here Si. There are some common variables, but there are some missing variables. There are some variables in Si which are missing in Xsj. So, what you can do is you can actually marginalize, get rid of them through marginalization. So, what that means is that over here you will carry out a summation over Xsi minus Sj, right, and that is exactly what this expression is actually telling you. And this Ni here, Ni is nothing but the neighboring nodes of node I. Okay. Is the set of neighbors of the node Xi. Okay. This is of course in this graph, in the junction tree. Okay. So, let us see if we can do an example. So, for the example I am going to go back to this the decoding of this code. So, let us select the page and copy it over. So, I want to give this a certain context. So, perhaps let us do the following. Let me insert a new page here in between and give you the setting. So, example of message passing. So, we are going to work with our 742 code, which has the parity check matrix that I introduced earlier. Okay, so perhaps I will put that down here. So, we want to decode this code, and let us consider the case when, say in an example, that the transmitted code word x is given by, well, I need to make sure that h times x is 0, but you can check that that is true for this example. Okay. So, what I am doing here is I am taking the middle force symbols equal to 0, and I know that that will work because if I add okay, there is something a little, there was an error in the matrix to begin with, sorry about that. These should have been zeros. I may need to correct it right in the beginning. So, let me go back and correct that. So, that was a typo that I did not catch. So, these should have been zeros. Okay. It is the same code that we had earlier, no change. So, if I look here in this code, I know that this vector here is a code word, because if I add the entries of let us say these columns 2, 3, 4, 5, if I add these columns, then I will actually get the all 0 column. So, from that I know that this is a code word. Okay. And let us assume that there is a single error. So, let us say that there is an error vector which is 0, 1, 1, 1, oops, I want to introduce just a single error. So, that is 0, 0, 0, 1, 0, 0, 0. So, I have deliberately introduced it in the 4th symbol. And now, my received vector will then be 0, 1, 1, 0, 1, 0, 0. Okay. So, this is the received vector. So, my aim is to actually correct this error here, okay, this error that was actually introduced, which means that this particular symbol was actually in error. Now, I will also assume that, so I guess I need one more page here. I will also assume that the channel is a binary symmetric channel. So, here are the crossover probabilities. And what I want to do now is try to pre-compute some quantities that we will actually be using. So, let me copy this over. And what I want to do is I want to compute so these symbols now correspond to 1 through 7, right. So, let me put down 1, 2, 3, 4, 5, 6 and 7. And if I am interested say in P of y1 given x1, I am interested in this quantity for P of y1 given x1 equal to 0 and then also as P of y1 given x1 equal to 1. So, that brings me to another comment that I need to make, that is in here the messages. So, we have given a formula for the messages that are passed, and you can see that these messages are functions of these messages are a function of certain variables. So, what does it mean to pass as a message a function of a certain variable? Okay, so, the variable can take on different values. So, what does it mean to say that I want to pass on a function? Well, the easiest way to do it, and which is the way we will follow, is just to actually say that here is a function of a certain set of variables. We will evaluate this function for all possible values of those variables and we will pass on that as a vector, we will write them down as a vector. So, in message passing you could think of the messages as being functions or you could think of them as being vectors which spell out the values of all possible values of the function. So, in our case in here, as it turns out, our messages are often functions of a single variable, like for example, when you are passing this this conditional probability as a message, then this is the kind of a message that you will actually end up passing. Okay. So, we will write this as a vector. Okay. So, we will just make a small comment here. This is typical in that it is a vector representation of the message of the function that constitutes the message. So, in this particular instance you can see that since y1 is 0, okay, you can actually evaluate this, and this is a binary symmetric channel. So, the probability of receiving a 0 given that you transmit a 0 is 1 minus epsilon, and this is accordingly epsilon. So, this is typical of a message that we will actually pass. However, when we pass messages, it is perfectly okay, because we are trying to pass these messages to make decisions about the variables, and your decision about a variable is not going to be altered if you actually scale all your messages by a universal constant. So, in this case what we will do is, for the sake of convenience, we will actually pick that universal constant to be 1 minus epsilon, and with that so we can put down here, and scaling by 1 minus epsilon yields the following vector 1 and theta, where theta is epsilon upon 1 minus epsilon. Okay, this is purely for the purposes of simplifying our computation. Okay. Okay, so with this introduction, I am now ready to identify the messages that are passed in here. So, just as, see, this is the local kernel associated with the node whose variable is x1, right. So, I think in identifying the local kernels, it helps to actually have in front of us the received vector. So, let us copy that over again, and I will put it here. Okay. So, keeping this in mind, so wherever we have a 0, the particular local kernel will be a 1 theta. Wherever it is a 1, what is going to happen is that the positions of the epsilon and 1 minus epsilon get interchanged. So, you will have a theta 1. So, wherever there is a 0, let us put down a 1 theta. So, these then are your local kernels. So, you have 1 theta, again you have 1 theta here at 4, and then again at 6 and 7. So, it is 1 theta, 1 theta, and for the other nodes we know that the local kernels are theta and 1. Okay. So, now we do not need this anymore, because we have got this figured out. So, I will remove that, and we will write this then is theta 1 and theta 1. So, these then are your local kernels. Okay. And message passing, now okay, there is another component of message passing which has to do with the schedule. Okay, so, if you go back here, I said that step 2 is pass messages along the edge of the junction tree in accordance with some schedule. Okay. So, here now the schedule, particular schedule that you adopt depends on how many objective functions you want to actually compute. In this case, we are interested in only one objective function. Okay. So, in that case what you do is, your next step is to actually orient all the edges in the graph towards the local domain whose objective function you wish to compute. Okay. So, let me put arrows on every one of these edges. Okay. So, now you have oriented all the edges towards the central node x 4 and you want to pass messages in the direction of the arrows. Now, this is the case, this will always be the case when you have a so called single vertex problem. So, in the case of the single vertex problem, there is just a single objective function to be computed. So, one orients all edges in the junction tree towards the corresponding local domain. So, that is exactly what we did, and now we pass messages. Now, remember what I told you earlier, that there is no memory, but it is most effective to pass messages when a node, see it's when you it is most effective if a node passes messages only once it has heard from all its neighbors. So, I will illustrate. So, for example, here this node, initially what will happen is that the local kernels like this node has not initially received any messages from either these two nodes. So, it is not quite ready to pass on a message to node 4. On the other hand, there is no harm in doing so, because node 4 can simply wait until it receives the correct message. Okay. But so, but on the other hand, you are just wasting a computation. So, if you did not want to do that, what you could do is you could actually start with those nodes that do have correct messages to report. For example, these so called leaf nodes in this tree have their local kernels, and that is all they actually report. So, I guess I should add to this that this message schedule is for interior nodes. So, what happens is that at the edges of the network, the message that is passed is simply the local kernel. Okay. So, I should perhaps add that somewhere. So, let me introduce here a note. Note the message mu I j x of S I intersect S j passed on by a leaf node is simply the marginalization of its local kernel. So, here, so in this expression here you can see that, because what we are really simply saying is that, look, if this node were a leaf node, then there would be no income edges nodes to feed into it. So, there would be no incoming messages. So, what it would do is it would simply take, it would multiply all the incoming messages together with the local kernel in general, but since there are no incoming messages, you simply take the local kernel and then you marginalize it as necessary and pass it on. Okay. So, that is all we are saying here. Okay. So, in other words, it fits into the general framework, but it is good to point it out separately. And so that is what will happen in our network. Initially the message that will be passed by each and every one of these nodes will actually be their local kernel. So, this will be theta 1 and 1 theta, and theta 1 and 1 theta. And similarly these nodes can also send in 1 theta and theta 1. Okay. And once they have done that, now at that point these parity check nodes, okay, are ready to pass their messages because they have received their incoming messages. So, perhaps what we will do next is we will copy this page and focus on the action at a particular parity check node. You have to be a little bit careful, make sure that I insert the page at the correct spot. I think I want it inserted at the edge. Let us see if I can actually do that. Okay, good. I think I am more or less successful. So, here I wanted to focus on just the computation that takes place at a particular parity check node. Okay. So, for that I want to remove all of this which is cluttering the view here. So, let us get rid of these, this part of the network. So, we have this. So, we are saying that look, and also I want to move this a little bit. So, let us move this. This is the local kernel, but let us move it here, let us say, and so the message that is passed here really calls for a marginalization. The marginalization is over x 1 and x 2. Okay. So, what you want to do is sum over x 1 and x 2 of p of y 1 x 1 p of y 2 x 2 times chi 1 to 4 chi 1 to 4 of x 1 x 2 x 4. Okay. And this is the function of x 4 that you wish to actually pass, this whole thing here. So, what does that mean? It means that let us say you are interested in x 1 x 4 equal to 0. Okay. You are interested in x 4 equal to 0, the value of this. That means that x 1 plus x 2 plus x 4, which must be equal to 0, forces x 1 plus x 2 equal to 0, which means if you choose x 1 equal to 1, you will choose x 2 equal to 0 and vice versa. Or if you choose x 4 equal to 1, then when x 1 is 1, x 2 is 0 or vice versa. Okay. So, with that in mind, this expression here simply means that based upon what we have here, that the message that is passed here, which is a marginalization of with respect to x 1 and x 2, is simply on the one hand it is for 0 I would take 1 plus theta squared, I would take 2 theta, that is I would take 1 in the theta and the 1 in the theta, or on the other hand I would take 1 plus theta squared. So, this entire computation here, keeping in mind that functions are represented as vectors, will result in this computation over here. Okay. All right. So, in fact, by symmetry, that is also the message that is passed along each of these other edges as well. And so, this diagram is getting a little bit crowded. but I think it's worth it to let's just take the extra effort to focus on one last computation. So now I want to focus on the computation here. So the computation that's so we know that each of the incoming messages by symmetry from the computation we did earlier is 2 theta 1 plus theta squared. This is also 2 theta 1 plus theta squared, and this is also 2 theta 1 plus theta squared. And then there is also the local kernel, we should not forget that, which in this case was let us go back and see, the local kernel was 1 theta. So what happens is that in the end what you want to do is, when you want to compute your objective function, is just simply to take the product of all the incoming messages along with the local kernel. So then your objective function that you compute is, and we just have 2 minutes left, so I will write this and summarize in the next class. So this turns out to be, what you are doing is you are just multiplying all of these functions. So that turns out to be 2 theta the whole cubed times theta into 1 plus theta squared the whole cubed, which, and remember that theta was equal to epsilon 1 minus epsilon. So this thing, since epsilon is small, right, this quantity is a small quantity, we can approximate this by just taking the leading term, so which is 8 theta cubed here, and theta here. We will neglect higher powers of theta in the denominator. So what this is saying is that, look, what I am going to give you at the end of this computation is the likelihood function of that we set out to compute right in the beginning, it was here, of x4 given y. And what we have shown at the end is this result here, which says that the probability that it is 0 is like theta cubed, the probability that it is 1 is like theta. So we think it is actually a 1, okay. But I will just quickly review it in the next class. So basically we have looked at a further example of message passing decoding, right. So we will stop here. Thank you.